So we've talked about how more electronegative atoms will pull electron density towards itself inside of covalent bonds. This means that every bond that isn't between two identical elements has an imbalance in its electron density. And that means that the gaining side will have a slightly more negative charge and the losing side will have a slightly more positive charge. Not a full charge, as they do in an ionic pair, but a more positive pole and a more negative pole. This creates what's called a dipole, a vector quantity whose direction aligns with the bond between the two atoms and whose magnitude is determined by the strength of the imbalance between the two electronegativities. A higher electronegativity difference makes the bond more polar. We determine the dipole moment of the overall molecule by summing together the dipole of each individual bond. Let's look again at water. Here we can see the structure of H2O. It's not showing the lone pairs on oxygen, but we know they're there, spread apart as far as they can be from each other and from the electrons on the hydrogen atoms. Oxygen has an electronegativity of around 3.5. Hydrogen is 2.1, telling us that oxygen will pull electron density away from the hydrogens and leave them with a partial positive charge. The oxygen atom will then carry a partial negative charge. This should create an overall dipole moment on the water molecule. Using the software, we can map the electron charge on top of the electron density that surrounds the atoms to see that there is a significant difference in charge between the hydrogen and oxygen sides of the molecule. This is the dipole moment, and this is why we say that water is a polar molecule. When we add vectors, those with equal magnitude but opposite direction cancel each other out, or they add up to zero. This means that not every molecule with a polar bond is a polar molecule, or has a dipole moment. In carbon dioxide, for example, the difference in electronegativity between carbon and oxygen creates a dipole on each of the two bonds. However, since these bonds are 180 degrees opposite to each other, and the CO dipole will have equal strength in both directions, the two dipoles cancel each other out, and we say that CO2 is a non-polar molecule. Now let's go back and look at our Lewis structures from last time and decide which of these molecules are polar and which are non-polar.